Road to Olympiad.
Welcome to RTO. Consider the following problem. Determine all order pairs mn of positive integers such that n cubed plus 1, the whole thing over mn minus 1, is also an integer. One common technique in determining whether an expression in fractional form is an integer is by simplifying the numerator and consider the situations where the numerator is divisible by the denominator. This can be helpful a lot of time because upon simplifying the numerator, it is usually pretty small, but in order for it to be divisible by the denominator, it needs to be greater than the denominator, which sometimes give us some nice bound to try out. Pause the video if you like to give this problem a try, and when you are ready, keep watching to learn how to solve it. To solve this problem, we start by considering two cases. Case 1, m is equal to n. Then, the fractions n cubed plus 1, the whole thing over mn minus 1, is simply equal to n cubed plus 1, the whole thing over n squared minus 1. The numerator can be factorized into n plus 1 times n squared minus n plus 1, whereas the denominator can be factorized into n plus 1 times n minus 1. This allows us to simplify the n plus 1 and get n squared minus n plus 1, the whole thing over n minus 1, which we can further simplify the fractions into n plus 1 over n minus 1. In order for this to be an integer, 1 over n minus 1 need to be an integer, or 1 need to be able to be divisible by n minus 1. This is only possible when n minus 1 is equal to 1 or n is equal to 2, which gives us m is equal to 2 as well. So we have our first solutions. Both m and n are equal to 2. For the second case, we have m is not equal to n. Notice that by the Euclidean algorithm, we can easily show that the GCD of mn minus 1 and m is equal to 1. This implies that mn minus 1 and m has no common factors other than 1. So we have the GCD of mn minus 1 and m cubed is equal to 1 as well. This is to say that by multiplying m cubed into the given fractions, it will not alter the integer property of the fractions. Or in other words, if n cubed plus 1 the whole thing over mn minus 1 is not an integer, so does the new fractions. But here, we can expand the bracket to get this one, where we can split the fraction this way. Notice that we split it this way to obtain the fraction m cubed plus 1 the whole thing over mn minus 1, where we will explain why we need it later. Here, notice that the numerator of the fractions on the left hand side can be factorized this way, and we can cancel off the term mn minus 1 to obtain an integer. Therefore, in order for n cubed plus 1 the whole thing over mn minus 1 to be an integer, we need m cubed times n cubed plus 1 the whole thing over mn minus 1 to be an integer, and this implies that m cubed plus 1 the whole thing over mn minus 1 need to be an integer as well. This is to say that any pairs of m and n that makes n cubed plus 1 the whole thing over mn minus 1 an integers, it will make m cubed plus 1 the whole thing over mn minus 1 an integer as well. And since they are just differ by interchanging the m and n, we know that any order pair, say a and b, that satisfy the conditions, we can just interchange the pair and we have b and a as another solution as well. Due to this symmetric property, it is sufficient for us to only discuss the case where m is greater than n, as the result when m is less than n will follow symmetrically. Here, if n is equal to 1, we have 2 over m minus n is an integer. This happens when m minus 1 is equal to 1 or 2, which give us m is equal to 2 or 3. So we have two more solutions, 2, 1 and 3, 1. And due to the symmetric property, 1, 2 and 1, 3 are the solution as well. If n is equal to 2, we have 9 over 2m minus 1 is an integer. By doing a quick check, only m is equal to 5 satisfy the conditions. And thus, we have the solutions 5, 2, as well as the symmetrical solutions 2, 5. For n is greater than 2, suppose that the fraction is equal to k. Where k is an integer, we have n cubed plus 1 is equal to kmn minus k. Taking congruent modular n, we have negative k is equal to 1 mod n, or k is equal to negative 1 mod n. This implies that k must be equal to pn minus 1 for some integer p. Then we have n cubed plus 1, the whole thing over mn minus 1 is equal to pn minus 1. Since m is greater than n by the assumptions, pn minus 1, which is equal to n cubed plus 1 the whole thing over mn minus 1, is less than n cubed plus 1 the whole thing over n squared minus 1, which is similar to the case 1 just now, where the numerator can be factorized into this one and the denominator into this one, and we can simplify the n plus 1 to get this thing, which can further simplify into this one. By rearranging the n and 1, we can factorize the inequality as follows. And notice that 1 plus 1 over n minus 1 is less than 2, as 1 over n minus 1 is at most 1. However, since n is greater than 2, it gives us no integer p solutions unless p is equal to 1. Back to the fractions, we now know that n cubed plus 1 the whole thing over mn minus 1 must be equal to n minus 1 since p is equal to 1, where we can rearrange into this one, adding 1 on both sides, simplifying the numerator, dividing n from both sides, we have m is equal to n squared plus 1 the whole thing over n minus 1, where we can simplify the fraction into n plus 1 plus 2 over n minus 1. Again, in order for m to be an integer, 2 over n minus 1 need to be an integer. But with the condition n is greater than 2, the only possible solution here is n is equal to 3, which gives us m is equal to 5. So our last pair of solutions will be 5, 3, as well as the symmetrical solution 3, 5. And these mark the end of our solutions. Post in the comment below if you have any thoughts on the video, and if you haven't subscribed yet, consider subscribing. This will really help us out. Anyway, see you in the next video. Thank you.